In this video, I will walk you through free response question number 4 from the 2004 AP exam. Consider the curve given by this equation. Part A says, show that dy dx is equal to this expression. So it looks like we are in for some implicit differentiation. So let's take the derivative of both sides of the equation with respect to x. Remember, when we are dealing with a factor or a term that involves y, we will have to use the chain rule. So the derivative of x squared is 2x. And then the derivative of 4y squared is going to be 8y using the power rule. But then, because this is not an x, we need to multiply by the derivative of the inner function, which means we have to multiply by dy dx. The derivative of a constant is 0, so that's gone. And now we're going to use the product rule on this term. So I will look at it as 3x times y. So I'm going to first take the derivative of 3x, which is just 3. And then I'm going to leave the second factor alone, so I have 3y plus. Now I'm going to go through again. This time I'm going to leave the first factor alone, so I have 3x. But I'm going to multiply by the derivative of the second factor, which is dy dx. Let's get all of the terms that involve dy dx on the left side of the equation and all of the other terms on the right side of the equation. So I'm going to leave 8y dy dx on the left side of the equation, but I'm going to subtract this term. So I'm going to bring this over to the other side, and it will become negative 3x dy dx. I'm going to leave the 3y over here on the right side of the equation, but I'm going to move this 2x over to the other side by subtracting that thing. So I'm going to have minus 2x. The point of having all the dy dx terms on one side of the equation is so you can factor it out as a GCF. So I'm going to bring dy dx out front of parentheses, and that will leave 8y minus 3x on the inside. So equals 3y minus 2x. Finally, to get dy dx by itself, I'm going to divide both sides by 8y minus 3x. So this will end up in the denominator. So I have dy dx is equal to 3y minus 2x over 8y minus 3x. And that's exactly what we were supposed to show, so that's it for part A. Part B, show that there is a point P with x-coordinate 3 at which the line tangent to the curve at P is horizontal. Find the y-coordinate of P. If there is to be a horizontal tangent line at point P, then dy dx must equal 0. So let's start off by setting the expression for dy dx equal to 0. So we have this, but a fraction will only equal 0 if the numerator equals 0. So that means that 3y minus 2x must equal 0. We are supposed to show that point P with x-coordinate 3 is the point of tangency that causes the slope to equal 0. So let's let x equal 3 and see what the y value is that goes with it. So we have 3y minus 2 times 3 is equal to 0. So 3y minus 6 is equal to 0, which means 3y is equal to 6 and y is equal to 2. So far we have shown that dy dx does equal 0 at the point 3, 2. But we're not done because we can't be sure that the point 3, 2 is actually on the original curve. So let's prove that. We can show that 3, 2 is on the curve by substituting 3 for x and 2 for y and verifying that we get a true statement. So that will give us 3 squared plus 4 times 2 squared is equal to 7 plus 3 times 2. So this will be 9 plus 4 times 4 is equal to 7 plus, well, this is 9 times 2, which is 18. So we have 9 plus 16, which is 25. And we have 7 plus 18, which is also 25. Therefore, the point 3, 2 is on the given curve. So we have shown that there is a point on the curve with an x-coordinate of 3 at which there is a horizontal tangent line. Part C, find the value of the second derivative at the point P found in Part B. Does the curve have a local maximum, a local minimum, or neither at point P? Justify your answer. So here's the first derivative from Part A. To find the second derivative, we need to take the derivative again. But I can see that the quotient rule is about to happen. Do you know the quotient rule poem? Low d high, less high d low. Draw the line and down below, the bottom squared will go. And every time I say d, as in d high, this means derivative. So here we go, low d high. Low means 8y minus 3x. So this is low. And then d high means the derivative of 3y minus 2x. Let's take it term by term. The derivative of 3y is going to be 3 and then dy dx. All right, basically we just leave the 3 alone and we just take the derivative of y. Moving on to the second term, the derivative of 2x is just 2. So this is low d high. So here comes less high d low. So this is high, the 3y minus 2x. D low is the derivative of 8y minus 3x. Term by term, the derivative of 8y is just going to be 8 and then dy dx. Now the derivative of negative 3x is just negative 3. So we have low d high less high d low. Draw the line and down below, the bottom squared will go. Next, we are supposed to evaluate the second derivative at the point P that we found in Part B. And that was the point 3, 2. So let's substitute 3 for all of the x's and 2 for all of the y's. But also remember that dy dx is equal to 0 at the point 3, 2. So everywhere you see a dy dx, we're going to substitute in 0. And sure, let's call this point P. So this is what we get after all of that substitution. Now we just need to simplify it down. So we have 16 minus 9, which is 7. And then we have 0 minus 2, which is negative 2. And then we have 6 minus 6, which is 0. And once that is multiplied by whatever's going on over here, the net result of this is 0. So this entire expression is gone. So I really don't even need the minus sign. And then in the denominator, this again is 16 minus 9, which is 7. We might as well go ahead and square it and put 49. 7 goes into 49 7 times. So this is going to be the same thing as negative 2 over 7. Don't forget that we are also supposed to say if the curve has a local maximum, a local minimum, or neither at the point P. So remember, if the second derivative is positive, then the curve is concave up. If the second derivative is negative, then the curve is concave down. If the curve is concave up, a horizontal tangent line makes the point of tangency a local min. If the curve is concave down, a horizontal tangent line makes the point of tangency a local max. In this case, we know there is a horizontal tangent line at the point 3, 2. So the fact that the second derivative is negative means the curve is concave down, and therefore this point of tangency is a local max. So here is our summary statement. The second derivative equals -2/7 at p, which equals 3, 2. Point P is a local maximum because the first derivative is equal to 0 and the second derivative is less than 0 at point P. Be sure that you have included both of these statements in your justification.